Okay. So first thing is I will start from the yeah, last week's ADS session. I'll complete that. There were some minute problems there in the ADS tutorial session. So I will address those issues and then we'll go to the filter section. Okay. And meanwhile, do you have any question? I would like to answer those first. Do you have any other queries or anything? Yes. Any? Yes.
Sir,
Yeah.
I have a question that can we get some more time because I have AWR software which is
Hmm.
provided by Cadence, but suddenly it's a student licensable. I have
Hmm.
got it, but it's crashed. I have mailed to Cadence to recover it. So
Hmm.
can I get some more time so it will help us?
Yeah, sure. That you will get because this is the first assignment, so you will extend it. Yes.
And sir, it's uh, complex, little bit complexable for me because it's my first project, and AWR software is little bit different from A's
ADS.
ADS.
Yeah. Different,
So
but it is similar only. My friend in the lab next to me, he works in AWR, so it is almost similar as I know.
okay, sir.
You have to, yeah, this you might find a tutorial anywhere, like YouTube only you can search, there will be a lot of tutorials and all, right? So it might not be very difficult, and the given the circuit is just a branch line coupler, you just have to add the components and do it. It's not like a very big deal. Yes.
Okay, sir.
Ah,
Okay, sir.
but
I will.
yeah.
Sir, which date I have to submit it?
Yeah, maybe I will extend it by 5 or 6 days. Yeah, you have to do by that. It's not like infinite time. Yeah, you have to do by next week.
Okay, sir. Thank you, sir.
Hmm. Yeah. Anybody else? So I saw a couple of submissions already. So one person, I forgot the name, but somebody submitted only the schematic. But I must tell you the schematic is actually nothing. You have to do the layout and microstrip circuit, not like just the add schematic components from ANSYS or ADS or AW or whatever and show the schematic simulation. Because that is obviously will not work in final layout. You must do the layout circuit, which should actually can be printed or fabricatable.
Hi,
Yeah.
yeah, hi, sir. I think that is me only. Actually, I just posted that thing. I couldn't get time much to work on, but now I have
Okay.
simulated even layout also. Only thing is like I
Mm-hmm.
have to means like prepare a report, like as
Mm-hmm.
you said, and
Yeah.
maybe I'll be submitting by tomorrow or so. Like
Ah,
I have done the layout simulation as well for that.
okay. Sure. Good. Yes.
Yeah, thank you.
Yeah. And yeah, as I told you, because you have to design yourselves. Unless you do that, this is not a theory class, okay? Although I am covering some theory so for your understanding. So just by reading the book and attending classes, you will not learn much unless you do yourself. So that is where the actual learning will happen. So that is where the assignments will come handy. And I will be posting almost in a weeks or 2 weeks interval. There will be like 3 or 4 assignments. So you have to do all of them. Then only you will get the certificate. Otherwise, you can just attend. But yeah, to get a certificate from this course, you have to do the assignments.
Uh, yeah, hi Saurav. And one doubt actually I have,
Yes.
like the duration of this course is like how much time? Like actually last week it started, I am aware, but I couldn't
Yeah.
attend that both the classes. But I
Hmm.
have seen the video recordings which you have shared, and then I started working on this assignment. So
Hmm.
like typically like how long it is planned? Like for 1 month,
It's planned almost like 6 to 7 weeks.
6 to 7 weeks. Okay, okay.
Yes. So 6 to 7 weekends, the classes will be done.
Okay.
So yeah.
So, like, then after the completion of all the classes and after submission of all the assignments,
Mhm.
then we'll be getting the certificate from.
Yeah, right. So it will take around 2 months. Yeah,
Okay, okay. And
yeah.
one thing, like as I told, I have done this thing. Now, actually, I want to prepare the report. So
Mm.
basically, what all things I have to put, like whatever the graphs and all which are implemented in that paper, same thing I have to plot in my simulation as well, and then I have to compare kind of both the things, like how it is expected.
No, see the whatever plot is given in the paper that you can just take from paper only. You can take a screenshot or snapshot
Screenshot.
from the paper and put it there. Yes, but your results you have to plot from simulation itself. Yes.
Yeah, means like I wanted to ask like what are all the graphs they have included in the paper? Same thing I also have to include in my report, correct? No, like from my
Not
simulation.
no no not all the things are not required. So see there will be like always whenever you are having a coupler, the S parameter plots you have to give. Okay, and the
Yeah,
another thing
actually,
is the
I saw they
yes.
have plotted even normalized frequency with respect to normalized frequencies. Also, they have plotted many things.
Yeah, yeah. So
So
there'll
there
be
I need to.
because that is a paper, they have to do a much more in-depth analysis, right? So if you
Okay,
can do that's fine, but
okay,
otherwise the
fine, fine.
final plots are only fine. So final results will be
Yeah,
okay.
main
Okay.
coupler
Uh-huh.
characteristics.
Yes, 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 yes,
Okay, okay, yeah, thank you.
yes. Yeah. Anybody else?
हा म्हणतो जवान जो खाते उठे हुए नक्की ते खबर पड़ती है कि छे नहीं कि जो जो जवान हम उसे ना खा बना सुना
Please mute your audio, whoever it is, Amit.
Sir, actually, the assignment, whatever you have posted, right, the topic was not covered. And today, power divider and coupler both will be covered.
Sorry? No, no, no. I will not be covering both. The see, theory is same for both of them, right? That is what you have
Okay.
to do only. Yeah. It's just the
Okay.
same lines, you have to add it similar ways, right? Yes. It's not much difference there.
Okay, sir. Okay.
But anyway, like I will address some of the issues of last week that I will show you now. Yes.
Okay.
Okay, so I will move on to that now. Let's see. Okay, so if you see last week, we were doing the schematic and layout, all we did. But then from layout to co-simulation results, there are some problems, right? So that is what I will go into now. So like, where was the problem? I think this screen I'm not sharing. Let me see. Okay, I think now you can see my ADS screen, right? Okay. So
Yes,
the
yes,
thing
yeah.
is, yeah, and the thing is, last week, while this problem happened, I removed the ports from schematic. So that is not correct actually. Because of that, the problem was happening. See this port 1, port 2, port 3. These ports are output ports. They will be definitely there. Along with this P3, P4 and P5 are the extra ports where you connect your resistance or any lumped element what you can connect in your circuit. Okay, so that is what this port should be there in the schematic. Because I removed it, that's why it's not working there. So now that this is there, so from the schematic I went to layout, right? If you remember, so this layout is I guess you remember all the setups there. You have to set up the dielectric substrate and as well as the other things. Frequency plan you have to set, okay, which frequency range you want to do simulation. And in the options, you can take cells per wavelength 20 and other things. Generally, you don't have to change much. Automatic things are fine. Then you can simulate it. Okay. Just simulate it. That is what we have done that, last week only. Right. So far, I guess you don't have any doubt. Do you have any doubt so far, like till this, till the layout? So if not, So when the layout results are declared, I mean layout results are generated, you have to make another schematic in the same cell. Okay, this is one cell. Let's say I make another schematic here. So this step you follow carefully. Okay, new schematic. Okay, cell 3. So I generated new schematic. Now how do I bring that symbol? So what is symbol? Symbol is, yeah, see this thing. Why this is important? Because this symbol is what will link the 3D EM simulation in layout to the schematic simulation. So this we have to bring to schematic, because in the layout we removed the lumped element, in this case which is a resistance. Now how we can add those is in the schematic only. So we have to bring this symbol to our different another schematic. That is what we'll do now. So this tip was not done properly last week. So you follow this how I am doing this one. So this new schematic file I have generated, you go to the top here, library say. Okay. So there you go, cell 3. If you just click on the cell 3 only, it will come. See, nothing much you have to do. You just have to double click on this. I will show this once again to you. See this here, all libraries, workspace libraries, inside that you go, it shows all the cells available in this project. So cell 3 is where we have done the layout simulation, and cell 3 is where the symbol is generated. How it is? Here you see, this is the cell 3 in my case. Here the symbol has been generated. So if you just double click on it, the symbol will, it will automatically come to this new schematic. Okay. So now that this is here, what you have to do? Nothing. You have to just, add the resistance and all to these ports. You see, all these ports are here, which the port numbers has been given there in the schematic. You have to now just add the resistance and all the other components. What we do in normal schematic. This is nothing, new or different. And here you see here shows, cell 3 IO, because this shows this has been imported. This sign will come only when you import a symbol to a schematic. And you will see in the results also it will show this same IO here. So this is 100 ohm here. Okay, so let's connect this to this guy here. So this, you see, the red connection has turned to blue. That means the connection is done properly. So similarly, we need port terminations. Simulation is parameter, termination 1 here, or 2 here, 3 here. So this, you see, this is normal. We add the ground here. We add the ground here as well. So these are the normal port terminations, 50 ohm terminations. Okay, nothing else. So see, all the ports we have defined. Termination 1, 2, 3. This termination will only define the port numbers for S parameter simulation. Okay. Whatever the number of termination, here you see termination number 2. This number 2 means this will be signified as port number 2. Now that all these things are set up here, we have to, this is nothing but, this is the S parameter machine. Let's say we set it 2 gigahertz, stop is 4 gigahertz, and this is 0.01. Apply. Okay. So now if we can just simulate, you can just run the simulation and it is done here. So now if you see the results here, see what happens. So S11, as usual, we get here, very good matching we got for 3 dB. If you remember, we matched everything we calculated using that line KL tool for 3 dB, right? So S11 shows a very good matching. As well as if you see in the result section here, you see how it is different. It shows IO.SP1. Why all these things come here? It's like, in the programming, you get a object oriented programming, you had dot this means like a structured thing, right? So here also, why is structured? Because first we started from schematic, then went to the layout, and this layout results are imported again to schematic. That's why all these things dot it comes. Actually, it says tells that the 3D EM results has been incorporated into the schematic simulation. So that is why only when this kind of the thing will come here. Okay. Otherwise, we will get only S22, S21 like this. It will show only schematic simulation. So that is not the final result. You should do like this. And also, if you see S21 and S33, both are very good, below 30 dB mostly. And similarly, if you can, want to see other results, let's say I want to see here, see all the results it come from the, so it connects the 3D simulation to the schematic simulation. Let's say I want to see S21, P1, because that is where the coupling happens, because the power division happens from the Wilkinson power divider. So we add that. So you see, so here we get the whole thing above 3.65 minus 3 dB. So it is very close to 3 dB because it is in a small scale range. It shows like a very big change. But actually, if you notice the scale is like less than 0.5 dB difference. So that means the power is close to minus 3 dB. So whenever whatever power you give at port 1, it gets divided to port 2 and port 3 in equal amount. Okay. So now I guess it is clear for you guys. So I will go through this once again. So you see, so we imported, first we have to draw the schematic here. Okay. Now, if it does not have any lumped element, so your work is actually easier. So you don't have to create extra ports to remove the lumped elements or not. But here it is, in your branch line coupler assignment, it will be actually easier. But I wanted to show all these steps because in the later on it will be required for you. Okay. So first you can do normal simulation without, with the resistance itself. Then if you remember, I did a tuning also. Okay. So those tunings you have to remember, it is possible only in schematic. As far as I know, it is possible in schematic. So first you do the simulation in schematic, complete simulation. You tune the results so that you get a very good results. And then you move to layout. You remove your lumped elements like here and create extra ports here like P4 and P5 where you can connect your lumped elements. Then you have to generate the layout. So the layout is here and you have to do a 3D simulation using this. You have to define substrate and all this. Then from the layout simulation, you can generate the symbol and this symbol you can import here in another schematic. And then you can do another 3D, another S parameter simulation that will give you the final result. So those are the steps. So now if you have any question, you can tell me. Yes. Ask any questions if you have here.
Once you go to schematic,
Once I will go to, yes, right. Yeah, right.
in this some one line is you merged now. What is that line? P4 to P5 port.
Oh, this is nothing. Actually, it is showing that there might be can be a connection. It is actually not a connection. It is giving a hints that there might be a connection missing here.
How you got this missing error?
Sorry, how I what?
You kept that ports, then automatically while simulation you
No,
got
no,
that
no,
error.
no. See, the thing is, no. There was no. Acha, last time you were saying how it happened.
Yes, exactly.
Uh-huh. See, the last time the thing is, if you remember, first we started from here, right? Yeah. So in this schematic, there are no P4, P5. Two ports are not there. We had simple resistance added. So there you do the schematic simulation and see if your results are good or not. Then you have to remove this one, right? You can just remove like this. You can cut it and remove it. But if you just remove, it is not sufficient, right? So how do you simulate these things here? You have to add two ports, so that you have to add two ports here at this two end. That is what P4, P5. So that in ultimate simulation, you can again add those things back, add the lumped element back. So yeah, that is the point. Yes.
Okay, what is the use of mesh?
Use of I don't know if you have read about electromagnetic simulation or not. So there are these are called computational method. So which can be done through FDTD or method of moments or finite element methods. So those methods, it calculates the current, surface current or voltage or electric magnetic field, all this. Based on that, this 3D EM simulation is actually carried out inside. Okay, that is another branch of study. Right. So for that, you have to divide your whole surface area into small pieces. Those are called mesh, where the current or electric or magnetic field will be calculated. And based on those, ultimate S parameter calculation is carried out. So you require this for 3D simulation.
Okay, give some rough idea for the three-way power divider. Just rough idea, nothing else. How to do, just rough idea.
Oh, okay, okay. So you see, the thing is, if you want to do extra circuit itself, so the one way is definitely you can add extra you can stack Wilkinson power dividers and all. Okay. Otherwise, I will just show you once. You know. See, this paper is from 1996. Okay. Yeah. See, this is one circuit they have done. 1, 2, 3, 4, 5, 6. So obviously, you see these papers are quite old. So the thing is, see, there is no hard and fast rule that this way only you have to make. There might be many possibilities available. Okay. Similarly, you see there are like lots of papers. Okay. So you have to basically look into the papers. If you want to have a different design, basically you have to search into Google Scholar and all. This is where I search. Okay. In Google Scholar. You can also search and look into the designs, these papers.
Okay, thank you.
Yeah. Okay. Anybody
Uh,
else? Yes.
Sir, good evening, sir.
One
Sir,
by one. Hmm.
sir, actually, when you are
Hmm.
going for EM simulation, you are removing the resistor, right?
We are
Between
removing.
I
Yes.
mean, the isolation. So after
Hmm.
that, you are performing the TM simulation,
Yeah. Right.
right? So
Hmm.
and here you are not placing any resistor value,
No.
if I am not wrong. So
Yes.
if you
Yes.
are
You're correct.
simulating, if you are not, if you are when you are simulating that result,
Huh.
okay, in EM simulation,
Mhm.
is there any changes compared to what you have done right now? No, you have converted to the symbol and you are placing the resistor. So now in EM simulation, you are not placing the resistor.
No, EM simulation you cannot place resistance. You can just do the 3D components all only. Okay, microstrip line and all this only you can do. Yes.
But is there any variation in result if you
Variation
are
in
not placing
result.
resistance in EM simulation?
Yeah, there might be a little bit change. Okay, might be a change. It might not be a very big. It will be very close.
Okay.
Yeah, if you do the design properly, the results will be
Okay.
close. Yes. And especially, the when the results will be good, like if you take a very lossy substrate and all, and if there are,
Okay.
uh, let's say when you have very thin lines and which may be
Okay.
capacitively coupled to each other, that means where mutual coupling can affect each other. All those
Okay.
cases, there might be a change in results. Okay, because this is a very simple circuit, it might not be a
Okay.
big change here.
Okay. Okay, thank you. That's
Yeah.
what.
Okay. Yeah. Next.
Sir, we have kept the cells per wavelength as 20. So,
Mm-hmm.
is there any rule of thumb that for this particular bit, this particular mesh size is optimum, or design to design, we have to always tune that cells for accuracy, something like that?
Yes, yes. See, generally the lowest you can take is lambda by 10. Okay. Lambda by 10 means
Okay. Mm-hmm.
cells per 10 cells per wavelength. Okay. That is lambda by 10 rule.
Mm-hmm.
But the better you
Okay.
take, like more cells you take, it is better. Especially if you have
Okay.
very thin lines and very sharp edges here. You
Mm-hmm.
see here the sharp edge. So there is better to take, more edges, more cells. So the simulations will be better actually. You know. See here you see
Okay.
the more cells you take, it will be more perfect or more accurate.
Mm-hmm.
You can take lambda
Mm-hmm.
by 20, that is good, or even lambda by 30 is also good. But for a big circuit, it will take a lot of time in simulation.
Yeah. Okay.
Yeah, okay.
Okay.
Next.
Some power dividers shows 2 or 3 resistors they are keeping.
Mm-hmm. Okay.
So what is the reason? May I know?
Now, see, the thing is, there is no end or no logic of a particular, I mean, why you should do that? See, you have to go into their design and read their logic only. There are many ways you can design a circuit, right? I am not saying this is the perfect design or this is the only design. This is one of the oldest design, one of the simplest. So,
In my office, some
uh,
designers do 3 cars or 4 cars for the 2 to 18 gigahertz. Like that,
hmm,
they are doing power dividers.
okay.
Is there any logic behind in that? Just I want to know. That's why.
No, no. See, wherever you have seen, it might be paper or something. They might be explaining that, right? Why they are designing. If that is not explained, you should not read that paper. So, yeah, one good rule of thumb is that you see here there will be like hundreds of thousands of papers. You should read papers from good journals, okay, or good conferences, not from anywhere. There will be, conferences or papers which are not very good way reviewed and all, so those things you should not see. You should see maybe which are good cited well and all. So they will explain also very well. Otherwise, other papers there is no guarantee that what they are saying will work or not. All right. Yeah. So read good papers only. Yeah. And that's why if you see that the paper I have shared with you for the this assignment is actually a paper from IEEE MTT microwave transaction. So which are one of the best journals in our domain. Okay. So those papers you can actually follow. That will give you. This will be very well explained with mathematical explanations and all. Yeah. Okay. So this is. The process you should follow and do the simulations. So some of you who are following other softwares, so I'm sure there might be tutorials available for them also. And that's why you should start from a very basic circuit. So I would suggest you can start from this Wilkinson itself. That might take you 1 or 2 days. Just follow the same steps I have done, get the results, understand the steps, and then go to the next one. Okay, directly you should not jump to a very big circuit. Okay, I have learned, I will do it now. So the small steps you should follow first. Basic things you do, then learn, and then go forward. Okay. So this is what I will close now. Now I will move to the next session, the filter session.
Sir, couplers you won't be covering. Later you will cover, because assignment is there, na?
No, coupler, the theory I have told, right? Coupler
Okay.
No, no,
theory
no,
I have. Yes.
no, sir. You didn't told anything on couplers.
I didn't. No, no, no. I have told you guys might have forgot.
No, we
No,
have missed.
last week I think he has told. I think.
Yeah. See, there is nothing much of a theory there. Okay, it's like the simple things only. You have to just do yourself. Unless you do this, that's why I shared the paper with you, where the theory is very well explained. Okay, you have to go through that only.
covered color, sir.
Yes, yes, I will show you. See, if you remember all this analysis I did for Wilkinson, right? So I told you the same thing is valid for four-port. If you remember this four-port network I explained. So coupler is nothing but a four-port network, right? Do you remember this or what?
You know the
Better
which
you go, yeah, you go through the video once again and you will understand.
which class? May I know the which class?
It will be the first class only, first class where the theory was covered. See, this here I have explained. Right? This is the branch line coupler you are supposed to do. Okay, and this paper they have done a newer version is better. So this is branch line coupler or 180-degree hybrid. This is rat race coupler. So this is just, there is nothing much of a extra theory or something you should learn. Only the lengths are mentioned. You should get the impedances here. That is what I mentioned. This z not 2 square root 2. This characteristic impedance will be required to calculate the line width, and then the line length is given already lambda by 4. This matrix, this theory is same, right? And that's why I shared the paper with you so that you read them and then understand. It's not like just do this blankly. I did not tell you to blindly do anything. You read the paper. The paper is like a 10 or 15 page. It explains everything from maths only. Did you? I guess you have the paper, right?
Yeah, yeah.
Yeah, you are supposed to read that paper, not like okay, how to do this, what to do this.
No, sir, it is actually 5 to 6 pages.
Yes, but does it cover analysis or not?
Yeah, yeah. It has like odd
Yes.
mode and even mode analysis, everything they
Ah,
have given actually in that.
exactly, exactly. Yes, yes. So I will just see here. I think in the slides only I had one or two slides. So the thing is, this design, and as similarly you have multiple other Wilkinson designs like this. See like this. These papers are also you can
Yeah,
see.
this one only. Yeah, exactly.
Yeah. So these papers are also there. So there are many more designs. Okay, you can just follow and read them there. So what I shared with you is this paper. Okay. So they said like they have a better design. That is why I followed with you. And this is a very recent paper also, just last year's paper. And this is the actually the ports. This is the simple branch line coupler. You can do this one only, or you can do this one as well. This is that the better one. And they provided length and all everything, even the line impedance and all. So if you actually calculate the line impedance, you can calculate from the Rogers substrate like this. That is your part. You have to do that. And then finally, you should get a design like this, the layout, and you should show the results like this. Okay. So you are supposed to do this simulation and show the results like this. This layout you are supposed to get. Yeah. Any more question?
Do you want to cover lump filters or triplet filters?
Yeah. Lamp filters as well as microstrip filters.
Okay,
See,
both.
only
Okay,
lump
thank you.
filter does not do anything, right? That filter, I
That
guess, in
going on
UG
filters on.
onwards, you are studying. Yes. Tell me. Yeah, yeah. Tell me what you are saying.
Nowadays is going with the not with lumped filters, only with the stripline filters only. That's why I'm asking.
Who is going? I did not understand. Okay, so I will start from the lumped filters because the theory is defined for lumped element. Okay. Once you know the theory, you can convert to microstrip or strip line, CPW line, SIW line, anything. Okay. So theory is same for all of them. Okay. Any other question? Okay. So we'll start here. Somebody asked a lot of questions. Okay. So somebody said that he sees, I think Maganti or he or she, I'm not sure. Anyway, it's like said that. Yes, I think I was talking about this submission only. So you have done only schematic simulation. So no, this is not fine actually. You have to find out other ways. Either you get the ADS software or any other software where you can do layout simulation. Okay, so only doing schematic simulation is not fine. So that does not show anything what you do because this is a RF thing, right? So only schematic means is doing as well as like CAD design, TCAD simulation, anything. This is nothing. You have to do layout. And you have asked, circuit does not has any reference or ground plane. It does have, right? I showed that the terminating resistances were terminated with a ground. And in the layout, what happens? So layout, we define a substrate, like, so we took the, if you remember, FR4 substrate. So by default, the other side of the substrate is ground, right? That is how microstrip line is defined. On the bottom of the substrate is ground for a microstrip line. So that is how it is the grounded. It is wideband divider. Yeah, you can tell it is wideband divider. Anyway, I will go to the next. But by the way, so I will be extending it for 5 or 6 days. But you have to find out and do it. Other because you got 1 week time already. So yeah, you have to find out ways and do it to get a certificate. Okay. So now we are coming to filter. Okay, so filter, as you know, it is very important in RF circuits or any circuits because many of the times we play with the frequency, right? So as you see, where is the main use of filters? In our communication transceiver circuits, we need low pass filter, high pass filter, band pass filter. Everything is required in a normal transmit receive circuit chain. Okay, so for before and after sampling, and in case of transmission before antenna, we use a band pass filter and all this. So basically filter design gives you that you can play with the frequency tuning. Okay, so some particular range of frequencies the circuit will give a good result, and for the other parts of the frequency you will have some other results. So you can tune the results with respect to the frequency. That is what you do in a filter. So filter, as you know, it means it filters out. So basic filters, low pass and band pass, I guess you have already learned, like, Chebyshev, Butterworth, and elliptical, all these filters. I suppose all of you have, studied about this in UG courses, right? So what is different here in microwave? So the main problem is the often is in the previous courses, what you have done, you have designed with RLC, right? ALC and R. So here, if you design like that, RLC, if you know here in microstrip, in the microwave frequencies, they do not behave like only RLC. In high frequencies, they become like there will be lot of parasitic elements coming up. Okay. So it is no more like a normal circuit behavior. The whatever you used to build circuits or filters with normal R, L, and C components, you cannot purely do that in microwave frequencies with simple RLC, because in high frequencies they will definitely bring out extra parasitics and other effects. So that will lead to the change in filters. So that's why. So how do we generally replace the RLC in microwave frequencies? If you have studied transmission line, you know that inductor and capacitor both can be replaced with a small section of microstrip line. I suppose that is the basic thing you know from your transmission line. If you take a lambda by 8 section of a microstrip line, it can, if it is open section, it will behave like a inductor, or if it is a short circuit in the other half, it will behave like a open circuit, or vice versa. So the gist is you can design a inductor or capacitor based on only on a small section of microstrip line. So that is what you have to use in microwave filters. Microwave filters based on microstrip line. Okay. And most of the frequencies, unless you go to very high frequencies and all, so it will work. Okay. So that is what we'll do. And if some of you might be, interested in millimeter wave and all this. So there the thing is you have to either use SIW line or CPW line. But the theory again remains same. How you implement them, that is different, but the theory remains same. So here in this course, we'll be covering microstrip line only. Okay. And as you know, it works very fine up to some several gigahertz. So that is why yeah, somebody was asking, what is the difference between lumped element and microwave filter. So I guess you now understand. Yeah. Do you have any question? Somebody asked that does ADS accept last plane as ground? Yeah, definitely it does. By default, the ground is defined there in the 3D simulation. Okay. So first, here we'll cover today the basic theory of the filters. Okay. And then we can move on to microstrip line based implementation. So just like other circuits, any other multi-port network, you can analyze them, these filters also, in terms of ABCD parameters. ABCD parameters is like in terms of voltage and current from the ports. You can analyze ABCD parameters for a two-port network or even other extra ports also. So the thing is, in microstrip line, what is another extra thing is that you have to match them as well. There might be multiple ports, all of these ports you have to match very well. So a matching network will be additional requirement. Okay. And the another terminology in microstrip line or any filter is image impedance. So what is image impedance? That will come to next slide. The thing is, if you have to do matching, this image impedance comes very handy, this concept. So generally using image impedance, we can explain the uh, filter network as well as we can derive the other parameters. So what are the other parameters? So any network, how do you define that it is good or bad? How do you analyze? So it is S parameter, right? So other than the S parameters, in microwave circuit or transmission line, there is another parameter called gamma or line impedance. Sorry, or mm, um, the line characteristics, which is gamma is defined as alpha plus JB, where alpha is the attenuation per unit length and beta is the phase length phase shift per unit length. Okay. So in terms of this alpha plus j beta, which is gamma, we can explain any circuit. So how they are relevant, we will look into that here. So even for normal circuit, I guess previously where you are doing the filter analysis, you are not looking into this gamma parameter or Z naught, the line impedance, characteristic impedance parameters. But here we have to do analysis in terms of that because in high frequency, we generally look into this. Now let's see. So let's say this is a network. Okay. So it might be a filter or any other network. It has two ports, V1 I1 is and V2 I2. So these are the voltage and currents, right? Now input impedance here in any term from inside or output in the other side, you can define in terms of voltage by current ratio, and that you can actually do in terms of ABCD parameters. Now this image impedance or this what is written here as in terms of ZI1 and ZI2. What are these? You see here also, see ZI1 and ZI2. So If you terminate the second port with Zi2, you will get an input impedance in first port as Zi1. Okay, so that is called image. Or opposite is the vice versa. If you terminate the first port with Zi1, you will get the output impedance at second port as Zi2. That's why it's called image, because it's just mirror image. If you put one resistance in one side, you will get another side another impedance, or the opposite. That's why it's called vice versa, or like it's called image impedance. These are Zi1 and Zi2. Zi1 is connected at port 1, or you can connect Zi2 at port 2. So these will be required to calculate the line input or output impedance. Now, as you know, there are some parameters or some properties of ABCD matrix. If you know from the network analysis or circuit analysis, you can just look into, it's not a big deal. For a passive circuit, A will be equals to D for ABCD passive ABCD matrix. So that's why if the network is symmetric, you can get Zi1 equals Zi2. So both sides you should have to connect a same impedance to get the image. Now you see the same analysis you can carry out for gamma. Now the thing is, how do you calculate gamma? So gamma is the propagation factor of the network. It can be defined in terms of square root of AD minus square root of BC. So which is the value of e to the power minus gamma? Where gamma is alpha plus j beta. So from this equation, this square root of AD, this you must remember. This is a very important equation. Okay. Now, okay. So from this equation, you can actually calculate gamma and corresponding alpha and beta values from the ABCD matrix. Okay. So the thing is, let's say a given network is given, a circuit is given, which corresponds of RLC or any other lumped parameter. You can calculate the ABCD matrix. From that, you can calculate the image impedance in the previous slide with this equation, square root of AB by CD, and gamma in square root of AD. If those calculations are done, so almost like half of the characteristics of microstrip line or a microwave filter can be done based on that. Okay. So those are the factors. Okay. So far, do you have any questions in understanding or any other theory?
I have one question.
Yes. Yes.
As you told in the previous class that at high frequency or microwave frequency, we used to consider S parameter only because voltage and current measurement is difficult. So why we are considering ABCD parameter? Because if we are considering voltage and current only, so why we are not considering S parameter, which is feasible at microwave frequencies?
Yes. Yes. Yeah. So yeah, very good question. Actually, yes. That if you are not asking, I was going to ask you the same question. So as I told you, so basic circuit analysis we do using ABCD parameter. Okay. And as it happens that the same circuit you can convert to microwave frequencies. Okay. Here we are not going to actually, high frequency, but I am saying these are the basic circuit analysis which you can carry out in terms of ABCD parameters. And then the same circuit you can replace the A and C parameters with microstrip line sections. Then it will be compatible with the normal circuit. Okay. I mean the normal microwave circuit. But the microstrip for the basic theory of microstrip, you need these ABCD parameters. That is how it is explained. Okay. And the another thing to a question, another answer is that if you look into the book, Pujar book, there is a transfer matrix which can using which you can convert ABCD matrix to S parameter or vice versa. Even you can convert Z and Y parameter to S parameter matrix and vice versa. Okay. So even though it does not hold, but you can do a analysis there. Okay. Even though S parameter is the perfect for us, still you can do analysis. It's not like, we cannot measure, but we can do the analysis. Okay. We cannot measure voltage and current, that is right, but mathematically we can do the analysis. That is what we are doing. Math, as you know, the many things we do in math, that is valid only in math, like complex numbers, which is does not actually exist. Like the complex real and imaginary part is there, only real part exists in real life, but still we can analyze things.
So means theoretically we can perform either Z or ABCD parameter analysis, but if we go to practical analysis like on softwares, so at there we have to perform S parameter analysis.
Yeah. So there obviously you don't have to calculate yourself. You can do the analysis using, because we are doing circuit analysis here, right? If you see here,
Yeah.
the basic analysis start from circuit, and circuits are very easy to analyze with the voltage and current. Yes.
So it is like KCL and KVL type of analysis, like we are doing, like how much current is going and what is the voltage at that point. So
Right. Similar, right. Yes. But only thing is now we have moved in terms of gamma and Z naught, all these parameters. We are bringing in the microstrip elements here.
okay, got it.
Yeah. Okay. Any other question? So by the way, most of these theories are taken from the Pozer book only. As I told you, microwave engineering by Pozer. You must follow the book if you want to, you want more in-depth analysis. Okay, you can follow that book.
Hello, sir.
Yes.
Hello.
Yes. Tell me.
Am I audible?
Yes.
I have a question about you said previously.
Right.
In RF microwave circuit,
RLC
circuits can be changed in microwave in microstrip line.
Right.
I have no doubt about resistor and inductor because they are pouches. How capacitor changed to microstrip line? Because it is a two plates separated by an insulator, while microstrip line is just metal.
Can you repeat the last part?
You understand my question?
Last part, can you repeat?
In capacitor, it is a two plates separated by just like when we embed one a metal. But it is not how it is transmitted to
capacitor, you are saying.
Microstrip line, because capacitor is an insulator separated by two plates.
Okay. See, the same thing is done in microstrip line. The insulator is replaced by the substrate, the dielectric object, right? The substrate in which you build the microstrip line is actually a insulator. It behaves like a insulator in high frequency.
Okay, the ground, the two plates, the ground and the
patches
are considered as a capacitor.
Yes, right. Actually, if you take a microstrip line of lambda by 8 length, and the other end of the microstrip line, if it is open circuited, then you get an input impedance which is equal to a capacitor. Okay. So if you have read the transmission line theory, you will understand that you can use both microstrip line for capacitor and inductor implementation. So I will ask you to go through the microstrip, the transmission line theory once.
Yeah. I missed the class. That's all.
Okay, no problem. Yes.
Thank you.
Yeah. Any more question? Okay. So now, with this background of theory, let's go into the analysis, circuit analysis, right? How we are going to actually implement the circuit. Let's start with a very basic circuit. Okay, let's take some impedances, which is Z1 by 2, Z1 by 2, and Z2. So this, if you see my mouse tip here, the first one, the red circuit, is called T network. And the bottom one with blue is called pi network. Hello? Okay. So the T network and pi network, so these are like, two alternate options you can implement in any one of them. Okay. So in both the cases, you can follow the previous equations to calculate ABCD. See, ABCD you can very easily calculate, right? Using these elements from voltage and current, like, KCL, KVL analysis you can do. And then you can first calculate ZI, which is the image impedance. Like what is the impedance value you can terminate for port 1 or port 2. And from the previous equations, you can also calculate e to the power gamma. E to the power gamma is nothing but the propagation factor. If you know e to the power gamma, from that you can calculate alpha and beta. Similarly, the same analysis you can do here also. The second circuit. ABCD parameters is very easy to calculate. Once you know this, then you can calculate ZI and E and gamma. These are the important characteristics in for the microwave filter. Now let's see how we can implement this Z1, Z2. A simple example is inductor and capacitor, right? We take Z1 as L and Z2 we take as C. So yeah, can anyone tell me how this circuit will work? What is the behavior of this circuit? Yeah, anybody? I am quite sure that this circuit you must have come across multiple times, right? How does
It's
this circuit behave?
it's low pass filter.
High pass?
Exactly. No, it's a low pass filter actually. Yeah. If you see inductor in the series, so it means that if you go towards lower frequency, it gives you very low impedance, so it will be like shorted. Now high frequency, the as omega increases, the impedance of the inductor increases, so it behaves like open, right? So this circuit actually from the normal analog circuit theory, it behaves like a low pass filter. Now we look into the microwave analysis. So how do we do the microwave analysis? It's simple. Simple thing is we have to calculate image impedance, ZI, and gamma. That is what we have done here. Like this is the general form. You can just put the Z1, Z2 value here in this equation, so you can calculate. So that is what we do here. See now, from the ratio of L and C, we can define a parameter called RO or K. This K parameter is very important in filter analysis, especially low pass filter, which is defined in terms of square root L over C. Okay. So when this is done, then you can just put these values here and calculate ZI and e to the power gamma. Now you see, there is a very interesting equation here. Square root of 1 over minus omega square by omega 2 square. Whenever you have a subtraction inside a square root, so there is a chance that it will be either real or it will be imaginary. Understand, right? Whenever you have a subtraction inside a square root, so it might become either greater than 0 or less than 0. So then together it will become either a real number or imaginary number. So what are the possible explanations for real number, imaginary number? Zi can be real or imaginary, and here also gamma can be real or imaginary. Okay. So can anyone tell like what will be the implication for real gamma and imaginary gamma? What will happen if gamma is real or gamma is imaginary? Is there any implication in microwave?
Real says it's reactive, resistive, and imaginary says it's reactive.
That is for the resistance. But I am saying from the microstrip or microwave circuit theory, or like just microwave propagation domain, you know what is gamma? Gamma is alpha plus
Yeah,
j
if
beta,
gamma
right?
is real, its wave is not propagating.
Hmm. Right. Yeah, right. Yes. So because gamma is explained as alpha plus j beta. If gamma is real, so only alpha is there. Alpha is nothing but attenuation. So it just attenuates the wave. It's kind of like behaves like a evanescent wave. Okay. And when this alpha terms is not there, then we have j beta. Okay. This j beta is, that means gamma is imaginary. In that case, the wave propagates. Beta is propagation constant. Okay. So phase shift per unit length. So in that case, we know that the wave only propagates. There is no attenuation. So this is called propagating wave. So in that case, wave will propagate through the circuit. So that's why this gamma calculation is so important. From that, you will know how much attenuation is happening or how much propagation is happening. Yeah, that's why that is the basis of all this analysis. Is there any doubt about it? Okay, so if not, then we can just analysis. We can analyze, here, if you see, for the expression of z I, we have square root of 1 minus omega by omega c square. In the expression of e to the power gamma, we have it opposite inside the square root. That means when z I is real, gamma is imaginary. That means wave propagates. And the opposite, when z I is imaginary, you have real gamma, because then it just attenuates. Okay. So that is what you should notice here in the theory, that the terms inside square root are opposite in gamma and Zi. So now in this circuit, coming back to this circuit, what happens that, if we take, k is the square root L by C is the 0, then we have, at omega naught, the Zi value becomes k only, because the previous term inside square root becomes 0. And for omega below omega c, when omega is less than omega c, that means in the lower frequency band, you see Zi is real and gamma is imaginary. Only when omega becomes greater than omega c, then gamma becomes real. So that is where the attenuation starts. So in that portion, it is called a stop band. When gamma becomes real, that means when the attenuation happens, there it is called stop band. So that is how we connect the traditional filter theory. There pass band and stop band, right? So there how we explain this using microwave theory. If you have a real gamma, or that means only alpha, attenuation happens. So in that band, you will have a stop band where your alpha is real, only have alpha, no beta. And where you have beta, no alpha, there you have a pass band, because there is no attenuation. So that is how normal circuit theory is used here in microwave domain, okay, for analysis. Do you understand this part? This is very vital. So the question always like, why we are doing all this? Why these analyses are required? So that is why, because in microwave domain we will be using this, propagation happens or attenuation happens in terms of gamma. If you remember, gamma is used everywhere in electromagnetics for propagation or in any circuit, any 3D structure, you will calculate gamma and all this, right? Is this part clear to you? Any question? So how passband and stopband is connected to
Actually,
gamma?
one
Yeah.
doubt I have.
Hmm. Yeah.
Like normally when we define EM wave propagation, like we also give the space parameter like e power minus gamma into z, like for the wave propagating in positive z direction.
Right, right.
Whereas in for negative z direction, it will be e power gamma into z only.
Right,
So
right.
in that sense, if we think this sign of gamma and correlating it with Zi sign, means like
Hmm.
that theory applies even for that condition also, or maybe
Yes,
this is
yes,
like
yes.
a more.
No, it's the same thing only. But you said this, if you take a jet, gamma and jet and all this. So see, there the problem is you deal with a very long distance, right? Generally, wave propagation on, you deal with some several wavelength distance and all. So there, part length, how much calculation is required. But here mainly we are bothered about the only alpha and beta parameters, okay, because we are not going to actually calculate how much actual attenuation happens or how much phase shift actually happens. Those we will do with s parameter only. But to if you have to analyze things with intuition, there these things will be required, okay.
Okay, okay. Like correlating like mathematically and
Yeah, right,
finding
yes.
out alpha. And
Hmm.
oh, yeah, understand.
Hmm. Okay. So now with that, this circuit is, this is a T network, and separately or similarly, you can explain this as a pi network also. So now, which one you will use. Sometimes it depends on how your circuit topology is and which one is easier to fabricate. All these things will come later. So there you have to decide which one to use, but both of them give the same results. So in this case, because below omega c is gamma is imaginary, that's why we have a pass band in lower frequency. So that's why it's called low pass filter. See, now if you plot this factor, k, as I told you, this k is a factor. This k factor is very important in filters. So which is in this case is square root L by C. That's why this particular filter topology is called constant K LPF, constant K low pass filter. Why constant K is that for a omega equals 0, if you put this K is not dependent on frequency. So actually it is not, this circuit K is not dependent on frequency. So that is why it's constant K. And you will see like how it is required or important. If you plot actually the alpha and beta, which are the constituent parameters of the gamma, for this frequency range, omega c for this filter, you see, till omega c, the beta increases exponentially and alpha is 0. And just after omega c, alpha it increases exponentially. There is no beta here. So now you understand, right, what I am telling you so far, why this pass band and stop band happens. So before omega c, less than omega c frequency, there is pass band because there is only phase beta parameter. There is no alpha or no attenuation. And just after the omega c, the attenuation starts very sharply. Okay. But there is no beta. That's why, the phase difference, the parameter is not there. Because the wave is attenuated after omega c or 3 dB cutoff frequency, as it said. So that's why it's a low pass filter. If you plot gamma, it will look like this. Is this part clear? What I have been explaining so far, this is what is here in this plot. You must understand this plot.
Yes, yes.
Yeah.
So even the pi filter topology also will give us a low pass only.
Low pass only.
Like
Yes,
depend.
yes. Yeah. See here, if you see in this slide only, first one is low pass filter, where L is in series and C are in parallel. But if you change the position of L and C, interchange, then you will get a high pass filter. It is just as simple as that. Just
Okay,
you see,
understood. Like
notice the two
series element
pictures.
L means low pass
Ah,
always.
exactly. So by interchanging L and C, you can create low pass and high pass.
Okay.
Yeah. Yeah. Any other question?
Hi. So even if after omega C there is not highlighted, but a pressure will exist, right? Is it because the with this?
Come again. Your first part was like very small sound. I could not hear it properly.
Yeah, and now it is clear, right?
Yes.
Yeah, so in the diagram, like post omega C, we do not have a beta highlighted, but beta will exist nevertheless, right? Phase difference will
Yeah.
still be
Beta will
highlighted.
exist. Yes, that is
Yeah.
right. Beta will exist, but
Mhm.
because there is very high component, very high alpha, so that's why it will be attenuated.
Okay, so it will be dominating basically.
Yes,
Uh,
right.
okay, yeah, got it. Thank you.
Mm. Okay, so now you tell me, can you tell that what are the other parameters we generally look for in a filter? We need pass band and stop band, right? This omega C is definitely a characteristics of a filter, which will be a cutoff filter, cutoff frequency. What else do you need generally in a filter? What are the other characteristics?
Like maybe roll off.
Yes, right. Another thing is roll up. So now, which parameter here in the plot will determine the roll up? Can you tell?
Alpha.
Yes, alpha is roll up. So yeah, right. Alpha will determine the roll up. Now here in this plot, you see after omega C, alpha increases. That will lead to the roll up. So what do you guess? How will be the roll up? Is it good or bad?
It should be like ideally means like we should have a very high roll off,
Hmm. But
but practically we cannot achieve.
from this plot, how do you think how it will be? Because you see here, right? It goes up slowly, it increases, right?
Yes, yeah.
So that means in this very simple filter structure, you will not get a very good roll up. That is what we generally want from a low pass filter. After omega C, it should have a drastic roll up, right? That is what we want. But here, if you see, just after omega C, alpha value is not very good. Alpha value is less only, just after omega C. If you notice here in this region, you
Yes,
you agree with or not? Right? I
yeah.
guess you understand the point here. See, just after omega C, alpha value is less. So that means you will not get a very good roll off in this region. But what we want generally
Correct.
for a high pass, low pass filter, we want a very sharp roll up. Just it should fall drastically after the cutoff frequency. For that, we need to modify this circuit. Okay. So this
Mm.
modification is called M derived low pass filter. That is what we will look into next. M derived low pass filter. This particular prototype is called constant K low pass filter. The next one, what we are going to look is called M derived low pass filter.
M derived.
Yes, it's called M derived because there will be another
Okay.
circuit component here. You see here the circuit schematic, the bottom one. There we have another component called M coming in. Okay. We are defining the circuit in terms of N. M. M is uh, M for mug. Okay. So this is what we are
Okay.
using. It's called a modification to constant K and it's called M derived filter section. Now the thing is we'll see what is this and how it helps. See, just adding a simple extra component, it can give you a drastic change. So that is where you should understand the theory always. See the previous one, the generalized theory was Z1 by 2 and Z2, right? Let's say we want to change this with Z1 prime and Z2 prime. But we want to keep the ZIT or image impedance same. So if the analysis is done in this way, Z1 prime is MZ1, M multiplied to the previous circuit what we have seen, M times Z1. So Z1 is nothing but the L inductor connected in the previous low pass filter. Okay. So using that, sorry, where did it go? Yeah. So you can calculate the formula of ZIT has already been given. You can put all this and you can calculate Z2 not prime here. So if you use the same formula, because we want to keep ZIT constant, then for a given Z1 naught, that is what we assumed as MZ1, we calculate Z2 prime. This is Z2M plus this. This is what is the revised circuit. See, Z1 has been replaced by MZ1 and Z2 is replaced with Z2 by M and 1 minus M square by 4M. This extra term has come now in the shunt element. In the shunt term, we have added an extra component. Okay. Now we'll see how it helps. The analysis is actually you can just calculate e to the power gamma. The formula is same. You have to put Z1 and Z2 all this. So this is like just normal. Now you know Z1, Z2, what are the values. If you put it here, you can see the calculation in the book anyway, nevertheless is there. Then you will get a plot like this. You see the plot of alpha versus omega frequency. This is the plot. Now here we have an additional term. It's called omega infinite. Or omega, what is omega infinite? It is defined as in this red, you see, it is omega c divided by 1 minus m square. And m is less than 1. M is taken as less than 1. So that means omega infinite is greater than omega c, where the response or alpha response is goes to infinite. It is very close to infinite. So that means you can create a extra pole here by putting this additional element in the shunt, where because of this at omega infinite you have additional pole. The alpha becomes very sharp here. Previously, if you remember, the alpha was going, slowly it was increasing. But because of this extra element put in the shunt term, we have a extra pole in omega infinite. It increases drastically after omega c because of this extra pole. Is this clear now how it is helping? And because of this extra pole, you see omega c drastically improves. So your roll off of this low pass filter will be improved very much only because of this section. A small section is improving your roll up. Yeah, is there any question here?
Okay. So like in the stop band only we'll see the impact of this M derived filter. Like the pass band will remain the same like constant K filter.
Yeah, almost same. Yes, almost same.
Okay.
Yes. Yeah. So because the main concern we had was the roll up. In the
Yes.
previous case, the roll up was not very good. Yes. So that is this analysis. If you do actually mathematical analysis, you can calculate from M, and from this the omega infinite value will be calculated, and the pole happens here. Okay. So that is why this is called M derived filter section. M derived because we multiply all the components with the M, and there is additional M section also. It's called M derived.
Okay.
Okay. Okay. So there is another factor here, which you'll see that generally for a normal low pass filter you can use the previous one, but you will not get a good roll up. But in this case, there is a problem that even though you get a good roll up, you see after omega infinite, the alpha value falls, right? Alpha value falls very much. That is another problem you will have in high frequencies. Although if it drastically falls for a good roll up, but after some time it does not fall very good. Okay. So that's why practically what people do, they take a cascaded version, they take a cascade of constant K and M derived. Both of them are used in a cascaded version. Okay. So this cascade is required because the M derived will give you very good roll up. But after some time, if because the roll up does not fall, I mean the attenuation should not fall. That's why the M derived filter section will be the constant K will be also required, because the constant K, if you see at high
It should
frequency
be.
is very high, right? So together with the M derived, it will give a good uh, attenuation at very high frequencies. That is required for low pass filter also. Yes. Any question? So yeah, so these plots are taken from the the Poser book. If you see here, the left hand side is the plot for constant K section, and the right hand side is for M derived T section. So as you see, the left hand side, the alpha increases slowly, but at high frequency alpha is very high. But here the right hand section is actually not only M, it's a composite of M as well as constant K. So if you see at the M derived section gives very good cutoff or very good roll up. After that, together both of them gives a very good attenuation at high frequencies also after omega c, after omega infinite. Is this point understood? That's why we need a cascade of constant K and M derived section. Yeah, is the point clear here? Why only one section will not work?
Yes.
Yes. Okay. Okay, somebody answer selectivity, insertion loss. Yeah, that is right. Those also will come to now. So far, this is the basic analysis of a filter. Okay. But now, as you know, everything cannot be calculated using basic math, right? You can have a intuition from this. That is how you have to go forward. Now, then how do you use calculate? You have to do, generally we use a Butterworth filter or Chebyshev or electrical filter. How do we do that generally? If we need a filter, generally it is specified in terms of insertion loss or return loss, all this. Okay. So how do we link that to the theory? So see, the in microstrip line or like any microwave theory, one of the main parameters is reflection, right? Or return loss. So which is defined in terms of gamma or capital gamma, which is nothing but the ratio of z omega minus z naught by z plus z naught, that you know from the transmission line theory, right? So you take the either input impedance or the output impedance of a network, and Z naught is the characteristic impedance of the transmission line. So from that you can calculate this formula with the gamma, capital gamma actually. Okay, this gives you return loss. Now from actually if you see the return loss is actually a even function. So that's why it can be explained, it can be actually written as terms of omega to the power 0, omega square, omega to the power 4, all these things comes because it's a even function. Okay, it's a function of omega square. So now why it is important? Now this PLR is called loss ratio. In the Poser book, they define it called loss ratio. Also, you can call it insertion loss also. It's similar. What is this term? Is the ratio of incident power to the load power. What is the power available from the source in the input side? What is the power available? And the denominator is power delivered to the load. How much power is actually then finally delivered to the load? And it is written as 1 over 1 minus gamma square. Actually, if you know, the gamma square gives you the reflected power, right? So if you subtract from 1 minus gamma square, P in into 1 minus gamma square is nothing but is the power delivered. And here insertion loss, we are actually taking the reverse. The source power comes in the top and the bottom is the load power delivered. So that's why, generally we write 1 minus gamma square is the power delivered to load. If you take that, this is just simple. It's put in the bottom in the denominator and the formula becomes 1 over 1 minus gamma square. That is the loss ratio or insertion loss. And if you write this from the in terms of previous gamma square, because it is the function of omega square 4, you can write is extend it in terms of m of two defined functions, right? M and n, which are both functions of omega square. And then if you expand this PLR, loss ratio of power or insertion loss, it becomes 1 over some function of omega square in the numerator and some function of n in the denominator. That is how you can write. And if you actually follow in the filter theory, you will see you will have some function for Butterworth filter and other functions for Chebyshev and elliptical also. That is how all these functions come. So basic is calculating the loss ratio or insertion loss. And the ratio is put like this. So if you put gamma square, value of gamma here, then from the reflection loss also, you can calculate this value, the loss ratio value. If you know insertion loss or S11, you can calculate the insertion loss. Which insertion loss is what? Is actually S21 parameter, okay? Is the magnitude of S21 parameter. If you give input at port 1, what you get at port 2 is S21, where the port 2 is terminated with 50 ohm. That is how S21 is defined, right? So amplitude of this S21 parameter is insertion loss. So the one difference you must remember, this insertion loss or return loss, they are not expressed in terms of minus. Normally S11 you can write minus 10 dB. S21 you can write minus 20 dB. But when you talk about loss actually it incorporates the minus sign already. You should not write return loss as minus 10 dB. You should write return loss as 10 dB only. Similarly, insertion loss as 30 dB. You cannot write insertion loss as minus 30 dB. That means it's actually gain. Okay, that you should remember. This is a very subtle differences there in terminology. These loss parameters, whenever you define, should not come with a minus sign. Okay. Now let's say we have to make a Butterworth filter. How do we do? This previous term, the M and N, this the expressions is already defined for Butterworth filter, which is called K omega by omega c to the power 2n. N is the order of the filter, okay, and omega c is the cutoff. So if you actually expand this, you see you can get the loss ratio at omega c. For k equals 1, P loss ratio is 2. That means half power will be delivered. At omega c, you get half power. Okay, that is how generally the cutoff filter cutoff is defined. Is to 1. Insertion loss will be half, 3 dB. And for omega greater than omega c, for a low pass Butterworth filter, you will get 20 n dB per decade roll up. dB 20 n. N is because 2 to the power n, right? That is how you get in log scale 20 n dB per decade. So similarly, the same expressions you also get for Chebyshev and elliptical filters also. This expression of m over n is given. So that is only you have to put and then you can calculate loss ratio. But the question or the problem is you have to synthesize the filter, not like, you are given everything, you have to find the loss ratio. Generally opposite, right? We want to calculate, or we want to design a filter for a given loss ratio. We want, let's say, minus 1 dB or minus 2 dB loss ratio filter. Within minus 1 dB, cutoff filter is this, and we have to design the filter. So this process is called synthesization. So how do we synthesize a filter? For a desired response is given, we need this parameters, so we have to design the filter. It's called synthesizing. How do we do that? You can, for a starter, you can start with very basic LC circuit again, and you put R as the load resistance. In this generator side, you can add a source, and the source resistance RS you can put as 1 ohm. Okay, so this is a very simplest Butterworth circuit possible. If you do this, you can calculate actually gamma, right? First thing you have to calculate is the capital gamma or reflection coefficient. Looking towards the LCR network, you can find out what is the input impedance. Once you know the input impedance, you can calculate from the input impedance what is the loss ratio. So these formulas are already given. Input impedance, if you know, you can calculate loss ratio. And let's say we want to calculate 1 over omega to the power 4. N is 2, right? N is 2 is what we are trying to calculate, second order filter. Then if you calculate all these things, you will get a expression in terms of, you get equation in terms of this R, C, L, everything. If you expand this, so for certain value of R, L, and C, you can get omega 1 plus omega to the power 4. You can get back to the expected Butterworth equation. So that's why this particular L, C, and R values you have to follow. By using this, you can do. This is the one simple way. But if you have to design, let's say, 8th order Butterworth filter, low pass filter, how do you do? You cannot, just calculate like that. So luckily, we are fortunate enough because the books and all other references, they mention a table. This table you will find in Pozar book and others also, I'm sure. So there they mention for a Butterworth filter or Chebyshev and all, they will have separate tables. What will be these components? For a particular order 1, 2, 3, 4, what will be this G1, G2 components you have to put? See, and the filter topology is like this: series and parallel, parallel, capacitor, inductor. You can put. So these components are given as a table, and your task is to put those and verify. Okay. And here you have to remember G naught is the first component here, is actually the component coming from the source resistance. And Gn plus 1, the last component is the load resistance or conductance. Okay. And the another point is all these components are actually normalized. It's like 1, 2, 1. These are obviously not the actual value of capacitor or inductor, right? These are normalized value. And we'll look into like how we have to calculate for your particular frequency. That is your task, your design. That is the problem of design. Okay. Any question from here?
Yeah, one thing like one doubt I have, like you said that gamma real, I mean, it's like the capital gamma is a even function, like powers of
Yeah, right.
yeah. How
Right.
do we justify that? Like means like with respect to like a loss you're telling, because normally we specify it as a loss only, so we will not put a minus sign while it's like in terms of minus we will not tell. So in that way, or how like
No,
how
no.
we
Yeah,
got
this
to this?
calculus. Yeah, this calculation, if you see, it is given here. So see, because gamma is a complex term, right? So if you
Okay.
see in a in the complex calculation, if you take a complex conjugate, then you will get another value. So if you can prove that complex conjugate is the negative of minus omega, then actually from here you can get, see, normal gamma calculation is R, Z, and all this term comes. And if you put gamma of minus omega, then you get some other value, which is actually coming as a gamma omega star. Now, if you
Okay.
take gamma omega square value, here see how it has been expanded. So a
Okay.
complex values square is you can take as gamma into gamma star, and gamma
Yeah,
star
yeah,
is
right.
gamma minus omega. So that is how gamma minus omega square. If
Okay.
a square is a minus square, that means it's even function of omega.
Yeah, yeah,
Yeah.
yeah. Okay, okay. Understood, understood.
Yeah. So this
Yes.
slide
Thank you.
is what? Yes. Okay. Anybody else? So this table you have to find in the Puzar book. Okay. So there they have provided for filter and all. And your next assignment will be actually needing all this. You have to find out all this and do yourself the design. Okay. I will show you a tutorial maybe next week, and then you have to do it yourself. Okay. So if it is done here, we'll move to the Chebyshev filter. Okay. So as you see, just like the Butterworth polynomial, you have another Chebyshev polynomial also defined. Although it is not as simple and straightforward as the other one, but the main characteristics remain same. If you see the Chebyshev polynomial also, it is a function of omega square, and you write it as 1 over k square Tn square. What is the loss ratio expression? So a similar thing you can calculate for R, L, and C values, and you will find a similar table in the book, which will give you the components J1, J2, G2, G3. Okay. Based on this, you can actually find out the values of L, C, and the other uh, capacitance and inductance values, so that you can build the filter network. Yeah. So far, as I told you, all these tables are a normalized table. So this will not directly give you the value of capacitor inductor. So to get the actual component, you have to uh, get back from the normalization. Okay. So the thing is, initially we have taken the source resistance to be 1, or R naught has been taken as 1. If the source resistance is not 1, you have to multiply this or divide by this thing, this. So these equations actually tell you if you have a defined R naught value, how your other values will change. LC values will change. And the other thing is, and the very important thing is, we have taken omega C as 1, omega over omega C as 1. Okay. So now you have to design for some particular frequency. You have to uh, change this omega over omega C component. You have to shift, you have to add a omega over omega C also to all your components here. So you see JXK, this, the capacitance or uh, admittance, all these values has to be multiplied by omega over omega C component for, let's say, some particular norm frequency you want to design. Okay. So that is how you get the values of LK and CK. You see, LK we get now omega C, and CK not CK prime we get omega C. Let's say your omega C value is you want to design at 4 gigahertz. You have to divide this previous value, what you get LK and CK, you get from the table. That you have to divide with 4 gigahertz to get actual value of capacitor inductor in your frequency. And if you combine with the R naught value, it looks like the rightmost pair of equations. So you understand, right? So what to do from the table? How do you get back the actual value of capacitor? How to calculate the capacitor inductor values for your frequency design of your frequency of design? So is it clear so far? Because today we'll stop here. Tomorrow we will look into two very important theorems. One is called Richard's transformation, and another is called Kuroda's identity. Okay, Richard's and Kuroda's identity. So here actually we will move from normal RLC components to microstrip line implementation. Actual RF implementation will start from tomorrow. So far is the theory. Theory remains same for low pass and high pass. Okay, we have to actually move. Tomorrow we'll start how to actually implement the circuits, RF circuits. So today we'll end here, and you tell me if you have any questions here. Otherwise, we'll end it here today. So by the way,
So
all
the
this
last
theory work,
slide,
yeah.
yeah, the
Tell me.
last slide, whatever currently, it's like you're telling the process of
Hmm.
taking the tabular forms for the particular Butterworth or Chebyshev filter, like what are the coefficients provided in the Poser book, and converting them into realizable values for our LNC values to construct a filter.
Actual filter. Yes, right. Yes.
So in this, like actually means like these are like steps, right? Whatever the screenshots we could see, like JXK equal to J into these are like progressive steps. Like step one, like finally we should arrive at this last value, whatever is
Last value.
present.
Yes, right. Yes.
Yeah, because I have doubt like if we are like using normally like thing like last if we see LK dash is equal to R naught into LK by omega C. So in that case, like if we see the unit twice, it's like a multiple of ohms with the Henry, and again you are dividing with the frequency. So can we talk in terms of for both left hand side and right hand side, the units will also be agreed finally?
No, actually, see, the units will not, these are not the normal units, because if you remember, in the microstrip line or like microwave transmission line, everything is a distributed thing. Okay.
Ah,
So it's not
correct.
just, simple L and C. Yeah. It's actually in terms of per unit length and other things. Yeah. Okay. I will
Okay, okay. So
clarify
if
that
we,
portion tomorrow. Yes.
yeah, fine.
Hello.
Yes.
Hello.
Yeah.
I have a question, sir.
Yes, sure.
What is the effect when we increase the order number of filters, like low pass filter or high pass filter?
Okay.
What is the effect when increasing the number of orders?
Okay, so generally, if you stack up multiple sections, you are supposed to get a better response in terms of the roll up will generally improve. Okay, you will get a better roll up. Yes.
Thank you.
Yeah, but that also comes at a cost of generally more loss. If you add more and more sections, your insertion loss will be also increased, but you will get a better roll up. Okay, that is where the actually trade-off comes. You have to make a trade-off of how much insertion loss is suitable for you and how much roll-up factor you want. You have to make a trade-off there.
Thank you.
Okay. Okay then. So tomorrow again we will continue in this time. Okay, 5:30. And so this is so far today. Okay. Yeah. Bye then. Bye.
Bye bye. Thank you.
Bye.
Thank you.
Thank you, sir.